Let's take some brief time to review our parabolas, and then we're going to add on some extension to it. Recall we have a parent function. It's the simplest form of any function. And for a lot of it, we're going to end up having a starting point at the origin. Now, a parabola can be defined by the graph of either y equals x squared, which is one we're used to, but also we could have x equals y squared. Later on, we'll also look at graphs of when we have both variables squared. Vertex is going to be kind of that starting point. It's either going to be the minimum or maximum on an x squared parabola, or on a y squared parabola, it will be the furthest left or right point. Axis of symmetry is going to be a vertical or horizontal line that passes directly through the vertex of the parabola. So when we look at a vertical parabola, we'll find that the axis of symmetry passes vertically through the vertex, giving us that symmetry or that mirror image across the parabola. On a horizontal parabola that opens left or right, the axis of symmetry will pass horizontally through the vertex. We're going to start by reviewing our standard vertical parabola. We're used to, or we've seen this form of the equation. Previously, we referred to it as vertex form, but more formally, it is considered standard form. This is often referred to as general form. There is another form of a parabola that's written as standard form, and we'll talk about that in detail later, but let's stick with these for now. Some important information about the parabola is that the vertex is located at the point h, k. Notice that there's going to be a sign switch on the value inside the formula. And the axis of symmetry will be a vertical line passing through x equals h. If our leading coefficient is positive, that gives us our dilation and the opening direction. Positive is up, negative is down. And if the a value is between 0 and 1, that means it's going to be wider than our parent function. If it's greater than 1, it'll be narrower than our parent function to give us our dilation. Now, if we're given an equation in general form, what we can do is complete the square to find the formula in vertex form, so we can identify the vertex as well as the axis of symmetry. Now, there are a few different ways to complete the square. The method that I choose, I find easiest, especially when we start to apply it to other types of equations later on. The first thing I like to do is take my parabola, and I like to set it equal to 0, and then go through the process of completing the square by moving the constant to one side of the equation and leaving the variables on the other side. And then I add in my boxes to remind me of the square. Recall that what goes in the box, our formula b over 2 squared. In this case, our b value is 4. Divided by 4 gives us 2. And when we square it, we get 4 again. So what goes in the box is the value 4. We've now created a perfect square trinomial that factors to be x plus 2 quantity squared, and the right side simplifies to 13. Notice what we're doing is we're trying to get the equation in the form where we have some quantity being squared plus whatever constant we have on the outside. And so we've done that by getting this binomial squared using completing the square. So the last thing we have to do is subtract the 13 to get it back to the same side of the equation. And then that's just our function. F of x equals x plus 2 squared minus 13. When we compare it to our formula, we see that our a value is 1, our h value is negative 2, note the sign switch, and k is negative 13. Since our vertex is h comma k, that means our vertex is located at negative 2, negative 13. And our axis of symmetry is at x equals h, which is going to be x equals negative 2. So we have the standard form of the equation, we have our vertex, and we have our axis of symmetry. Let's briefly talk about some of the other features of the graph. So we know that we have a starting point at -2, -13. And based on the leading coefficient, it has an a value that's positive, which means the parabola is going to open up. And we have an axis of symmetry that's running through the vertex. Some other things to note is the domain and the range. Well, with all of our vertical parabolas, the domain being all the x values, well, this graph is forever going to the left and to the right. So the domain is going to be -infinity to infinity. And again, that's going to be true for all of our quadratic parabolas where we have x squared. The range, however, with the y values is dependent upon the vertex. Well, since the vertex gives the minimum point at -13, our range is from -13 to infinity. And all of our vertical parabolas follow a pattern where the domain is all real numbers, but the range is either going to be -infinity to k or k to infinity, depending on the direction that the parabola is opening. And so you'll see this consistency with all of our vertical parabolas. Let's take some time now to do example B. So here we have our function, and we'll start out again by setting our function equal to 0, just for ease of evaluating. And we move our constant to the other side of the equation. Now, before we go ahead and fill in the box, we have to take care of our leading coefficient, and we need to factor it out. X squared minus 2x. But because we factored out that leading coefficient, we need to remember to multiply by 2 on the other side of the equation. Now we can fill in the value for our box. Using b over 2 squared, our b value is now 2. So 1 squared gives us 1. Now we can factor. Our perfect square trinomial factors to be x minus 1 squared. Our leading coefficient comes down, and then the right side simplifies to 1. We bring the right side back over, and then that's our function, g of x. So we have an a value of 2, we have an h value of 1, and we have a k value of -1. Our vertex is going to be located at 1, -1, and our axis of symmetry at x equals 1. And so if we compare it to our other graph, we have our vertex at 1, -1, with our axis of symmetry, and it's also going to open up, but it's going to be narrower because that a value is greater than 1.